and get started with today's material. So today we're continuing now the actual development of our logic. We just barely did 2 big deep dives into axiomatic systems, trying to get you comfortable with what these things are and get you comfortable with just constructing proofs, constructing derivations in them. So this next section now, we're going to go into interpretation and validity. How to interpret sentences. Now we've used this word interpretation before, but we were talking about sentential interpretations. A sentential interpretation. So reminding you all the way back, what is a sentential interpretation? So going way, way back before we had our full grammar, we were dealing with sentences that look something like this, right? Where A, B, and C themselves all represented sentences. And this might have been the sentence like, all animals need food and all bumblebees make honey. Or if all animals need food and all bumblebees make honey, then all cats are afraid of dogs. And that might have been the encoding of that sentence. What's a sentential interpretation of that sentence?
You can replace any of the terms.
You can replace any of the sentences with any other sentence you want. And what you have to preserve is the overall structure. Every interpretation has to preserve that and has to preserve that implies, being your highest level sentential connectives. And so one interpretation of this sentence might be a sentence that we symbolize this way. Notice that it still has a sentence, and a sentence implies a sentence. Where the D, E, F, H, and I could be whatever sentences we make up. So this is a sentential interpretation of that. What do sentential interpretations preserve? The sentential connectives applying to sentences. That's what they preserve. So up until now, we've only been talking about sentential interpretations. We're going to introduce now the notion of just an interpretation. An interpretation is going to be a stricter notion than a sentential interpretation. With sentential interpretations, we were able to talk about something called a tautology. What was a tautology? A tautology was a sentence that was true under every sentential interpretation. Or in other words, something was a tautology if no matter how I replace those sentences, it was always true. Since sentential interpretations is just replacing these sentences with true or false sentences, we can always check if something was a tautology with just a truth table. So how would you know if something was a tautology? Build a truth table for it. And if this were a tautology, then this piece right here would also be a tautology. If this were a tautology, every interpretation of it would also be a tautology. Now it turns out that this isn't a tautology, but if I would have given you a sentence like A or not A, you could create any interpretation now, any sentential interpretation of this now that you want, and it would also be true. This is always true, and come up with any interpretation. Whatever you replace the A here with, doesn't matter how crazy you get with it. We can replace it with a B implies C if we wanted. Well, we have to replace the same A, the same thing with that A there. So it would be or not B implies C. And this would be an interpretation of that. And since this is always true, this is always going to be true. So if every sentential interpretation is true, then you have what we call tautology. So we use sentential interpretations to identify tautologies. Doing truth tables was logically equivalent to checking sentential interpretations, checking all the sentential interpretations. That's what the truth table is doing. Because when I replace that with a sentence, every sentence has to either be
True or false.
True or false. And that's what we did with the truth table. Let's handle the case where I replace that with a true sentence, and let's handle the case where I replace that with a false sentence, and see how it comes out. Because that's all you can do in a sentential interpretation. Replace a sentence with a sentence, and that sentence is either going to be true or false. And that's all you can do. So that's what we were doing with truth tables. Now, we've already talked a lot about how truth tables don't give us enough. We can't prove everything that we want to prove with truth tables. We need something broader than that. So tautologies were a good start. What we're going to move up to now is the concept of something being universally valid. If it's a tautology, it is for sure universally valid. But the converse will not be the case. So, remind ourselves, here's some sentence. I say for every x, either X is red or X is not red. Is that sentence true?
Yes.
Yes, and hopefully it appeals to your intuition that that's true. If we were to symbolize it just using this notation up here, we would just have to symbolize this all as one sentence, R. There's no way that we could break it down more. This is not oring together two different sentences. This is not saying the same thing as R or not R. That is not what this is saying. Right?
It looks like that's what
Saying
it's
for
saying.
all X, you have to, and
This is saying for any particular thing you choose, either that particular thing is red or that particular thing is not red. If you pick R to be some sentence like everything is red, this says everything is red, or it's not the case that everything is red. That would be very different than what this is saying. This is saying take a particular thing and it's either red or not red. There isn't some sentence R, you could write out R equals, write the sentence there, such that this says the same thing as that. Because the subject of this is the same as the subject of that, so to speak. And they're somehow related to each other, instead of being separate sentences. And so if we were to just have our grammar limited to this, this is the only thing we can do to symbolize it. Just throw a letter on there and that's all we can do. And so we've introduced now more to our grammar. So our grammar, we start out with parentheses and sentential connectives, which is what we were using up here. And then we went on to add terms, predicates, quantifiers. And that was our full grammar for symbolizing sentences. And we actually finally gave a full definition as to what a sentence was. Remember our definition of a sentence? A formula with no free variables. So it's essentially going to be a formula that you can call true or false. Anyways, and then with our full grammar, we can now take this and symbolize it like this. For all X, either X applies to red or not. Sorry, red applies to X or not red applies to X. And this symbolizes this. This is not a tautology, but it is universally valid. A tautology is a stronger notion than universally valid.
is it because it has a quantifier?
Well, it's just because a tautology is something that we can symbolize like this, and it's always true. A tautology means it's true just by its sentential connectives. Universally valid means when we consider all of its logical structure, then it's always true. We're not just looking at the sentential connectives. If the sentential connectives alone make it true, okay, then it's universally valid. But maybe you have to dig deeper than that, and it's actually deeper in its logical structure that it's always true. And that's what universally valid is going to get at. That's kind of high level what we're going to be talking about. Good? Any questions so far? Before we jump into our definition of interpretation now? All right, we'll jump to our definition. So, what is an interpretation? So here's our definition. Sentence S, it's a sentence, so it has to be a formula with no free variables. Every interpretation is going to be a sentence. Every interpretation is going to be a formula with no free variables. Sentence S is an interpretation of a formula F with respect to the domain of individuals D. This is the first time we've talked about that. From here on out, when we come up with some interpretation for a system, we have to specify the domain that we're talking about. So sentence S is an interpretation of formula F with respect to the domain of individual D, the domain of individuals D, if and only if S can be obtained from F by substituting predicates and operation symbols defined on D for predicates and operation symbols in F, and by substituting constants in D for constants and free variables in F. Okay, that is a giant mouthful. We'll do some examples, we'll read it again, and I think it'll click. Because as big of a mouthful as that is, the idea is pretty simple. Just replace predicates and operation symbols with predicates and operation symbols defined in our domain. And that's interpretation. So let's do an example. Here's one of our axioms that we've gotten very comfortable with. This is our axiom from weak preference. And we're going to come up with the interpretation for it. So this, in our definition up here, is F. Here's the formula that we want to create an interpretation for. This formula happens to also be a sentence, because it has no free variables. But it didn't have to be. So here's a formula. We are now going to create an interpretation of this formula. You with me? So I'm going to let our domain be all real numbers. And our interpretation will be, for all x, for all y, for all z, x less than or equal to y, and y less than or equal to z, implies x is less than or equal to z. And this here is our S. This is an interpretation of that, where D, our domain of individuals in this special case, D was, hopefully you remember the symbol, it's R with an extra line on the left-hand side. That means a set of all real numbers. Set of all numbers. There's our domain. Less than or equals is a predicate defined on the real numbers. So here's my formula, and I replaced predicates in my formula with predicates defined on my domain. You with me?
So predicates like are relations sometimes?
A relation is a two-term predicate.
Okay. Yeah.
Does that mean that predicates are sentences?
Sorry, what?
Predicates are a sentence?
They gotta have a.
No. Standard predicate, we just use the greater than or equal predicate.
Well, when I was asking you about the sentential interpretations, I said you replaced all terms, and then you said you replaced all sentences.
So A here does not represent a predicate. It represents a sentence. And then when we switched to our full grammar, we said from here on out, capital letters represent predicates. They no longer represent sentences. Thank you. Up here, each letter represented a full-fledged sentence.
Okay.
And we didn't have a way to symbolize that sentence because we didn't have our full grammar yet.
I gotcha.
So good. Up here, capital letters were representing sentences. When we got our full grammar, we said, we're changing our symbolization now. We're never going to symbolize full sentences with just one letter. We're going to break them all the way down, capture their quantifiers, their terms, their predicates, and we're now going to reserve capital letters for predicates. What is a predicate? What's the basic idea of a predicate?
It returns as true or false. And
It returns a true and false. It's a proposition valued function. You give it terms and it spits out a proposition. You give it terms and it spits out true or false. This is the greater than or equal to 2 predicate. You give it 3, it spits out true. You give it 1, it spits out false. This is a greater than or equal predicate. You can also call it a relation because it takes 2 terms. If you give it 1 and 3, it spits out false. If you were to give it 3 and 1, it would spit out true. Predicates are proposition valued. Make sense? Okay. So in our interpretation, notice here, we didn't have any free variables. We didn't have any operation symbols. We only had predicates. So in my interpretation, I only replace predicates with predicates defined on our domain of individuals. You with me? We have to replace 3 things: free variables, operation symbols, and predicates. This would only have predicates, so that's all we need to replace in our interpretation. And now we can continue with the same interpretation for this one. What would be an interpretation for this sentence? We can simply say for all x and for all y, x less than or equal to y, or y is less than or equal to x. There's an interpretation. I could have also created a different interpretation. For all x and for all y, x is less than y, or y is less than x.
No.
But that's false.
Yeah.
So it's a false interpretation. It doesn't mean it's not an interpretation. So, read our definition one more time. Sentence S is an interpretation of formula F, here's S, with respect to the domain of individuals D, if and only if S can be obtained from F by substituting predicates and operation symbols defined on D for predicates and operation symbols in F, and by substituting constants in D for constants and free variables in F. That's right. Go ahead.
What do you mean by operation symbols exactly?
So this one didn't have any operation symbols. Let me give you an example. Here is a typical operation symbol, plus. Plus is think about the difference between less than or equal and plus. If I give you two numbers on this, it spits out true or false. If I give you two numbers on this, what does it spit out?
A result, like
another number.
Another number.
So operations take terms and spit out terms. Predicates take terms and spit out propositions, spit out true or false.
Oh, okay, that makes sense.
So those are we've got three types of symbols. We've either got our symbols that represent terms, we've got our symbols that represent operation symbols, or we've got our symbols that represent predicates. And those are the three symbols that we use, outside of parentheses and sentential connectives.
Okay.
Oh, and quantifiers. Okay. So these ones, we're starting out with ones that just had predicates to replace in our interpretation. So an interpretation of this, let's call that F. Let's come up with the interpretation of this. For all x, for all y, what? Give me something.
X is greater than y.
X is greater than y, if and only if.
X is less than y.
X is less than y. And
Y is less than x.
y is less than x.
If we replace the I with an equals, maybe that's
So there's a false interpretation.
okay.
We could have made a true interpretation. We could have called that equals, less than or equal, less than or equal. Okay, now it's a true interpretation. But interpretation doesn't care if it comes out true or false. An interpretation is just an interpretation. And so the fact that these things have interpretations that are true and have interpretations that are false means that none of these statements alone are universally valid. Right? All right. One more. For all x, for all y. Give me interpretation.
Equals.
X equals y is logically equivalent to not. You don't get to replace those. Very important here. We only replace predicates, operation symbols, and free variables and constants. We don't replace any of our sentential connectives. We don't replace any of our quantifiers. So have to keep the not there. And then what?
Less than.
Y less than x. There we go. There's an interpretation. An interpretation that's not true, but an interpretation. If we want a true interpretation, we could have said x less than y means that y is not less than or equal to x. There's a true interpretation.
You mean greater than?
X less than y means that it is not the case that y is less than or equal to x.
Well, no, it's x is great. Oh.
You want to say the x first.
No,
We're
no,
saying the
that's-
same thing. You want to read that as x greater than or equal to y.
No, I read it as xy and then xy again and not xy and yx.
Oh,
I
I
got
see.
flipped in my mind.
All right. And then finally, one more here. One of the theorems that we proved, every theorem also has an interpretation. And we can do x less than y implies it is not the case that y is less than x. There's a true interpretation. You with me?
Mm-hmm.
Now, we proved theorem 4 as a theorem. What does that mean? That means that we showed, I don't remember what axioms it depended upon. Let's pretend that it depended upon axiom 1 and axiom 2. I don't know if that's true. But we proved theorem 4, meaning we showed axiom 1 and it would have used definition 1 or definition 2 somewhere along the way. So we'll pretend it was axiom 1 and definition 2. We showed that those together implied theorem 4. That's what we proved when we were doing this system, right? Something like that. Now notice that axiom 1 is not universally valid. Definition 2, not universally valid. Theorem 4, not universally valid. However, axiom 1 and definition 2 implies theorem 4. That is universally valid. If you came up with an interpretation that made those true, then your interpretation of theorem 4 would also be true. If you interpreted the whole system in one go. If you came up with an interpretation that made these false, false implies anything is true. So if you come up with an interpretation that makes those true, then that is going to be true under that same interpretation. And if you came up with an interpretation that made those false, who cares? It's vacuously true. And so when we're doing our proofs, we are demonstrating that they're universally valid. Prior to this, I was saying that when we prove something, we show it's a tautological implication. That was kind of a lie. Really, when we prove something, we show that the implication is universally valid. Now that is strictly true. No half-truth in there. That's the full thing. That's what we do. That make sense? Okay. So got the point I wanted to get across there. From here on out, just some exercises coming up with interpretations. So now let's come up with interpretations.
X is equal to y.
So if x is equal to y, let's try and keep it true. So we'll say if x is less than y, then for all z, if x is equal to z, then z is less than y. Okay, that is a true interpretation, right? If x is less than y, then for all z, if x equals z, then z is less than y. Is that a true interpretation?
Yes.
No. What's our problem?
Three variables.
Free variables. Sentence S is an interpretation of formula F. We are trying to claim that S here is our interpretation. What does S have to be? A sentence. This is not a sentence. It is an idiom of the English language that when a quantifier is not provided, you automatically think in your head, for all. And so you were interpreting this as for all x and for all y. Then, all that. And now, that is a sentence. But x less than y by itself, true or false? X less than y. Yeah. Bad question. Up here we were saying if x is less than y. You're used to that language from algebra because we speak imprecisely, but x less than y is not a proposition. You can't call it true, you can't call it false. So now that we put those quantifiers on there, now this is an interpretation of that, right? No!
Because you added
We can't just add quantifiers willy-nilly. So no, this is still, it happened to make it a sentence, but that doesn't magically make it an interpretation. So we're still in trouble. So get rid of that. We can't just add quantifiers whenever we feel like. So here's what we had. So what can I do to make this thing an interpretation? So let's read our definition again. Sentence S is an interpretation of formula F with respect to the domain of individuals D. Let's assume that our domain of individuals was all real numbers. If and only if S can be obtained from F by substituting predicates and operation symbols defined on D for predicates and operation symbols in F. So we did that. And by substituting constants in D for constants and free variables in F. So I have to replace every constant and free variable in F for constants and free variables in D, or for constants in D.
So you can make x, y a constant?
So I need to make x and y constant. So what should I replace x with? 3. That works. 3 there. We better make it a 3 here. And what should I replace my y with? 4. And there we go. That is now a valid interpretation. And it happens to be a true interpretation. If 3 is less than 4, then for all z, if z is equal to 3, z is less than 4. Make sense? Mm-hmm. Okay, I think that one right there was probably your biggest gotcha. Is oftentimes when we read free variables, we don't really interpret them as free variables in our brain, and we're okay with it just because of how the English language reads. All right, so next one. Let's come up with an interpretation for this one. For all x and for all y, x plus y equals y plus x. We have to keep our quantifiers the same, so don't mess with those.
And we have to keep our operators the same?
Nope. We replace our operator symbols with whatever we want, and we can pick whatever domain we want. What domain of individuals do we want?
Rationals.
The rationals, okay, so we'll use rational numbers. There's a symbol for the rational, so we're basically just using numbers, fractions. That's fine. What's an operation symbol defined on fractions? Divide. So we can say x divided by y equals y divided by x. Right?
Yeah.
Almost. We're in trouble now. You happen to pick the one operation symbol that isn't defined on all the rationals.
Oh, yeah. That's
For the sake of not having to think about it and not deal with dividing by 0 right now, let's just pretend that we chose times instead. And then we can keep our domain of individuals rationals. And we won't have that conversation about how we deal with dividing by 0.
But we didn't care that it wasn't true. That wasn't the problem, right?
Right. The problem is that you made so that a term comes out that wasn't in our domain.
Undefined.
That was, undefined.
Yeah.
We would have a similar problem if we called this the naturals and we used subtraction here.
Oh.
Because 2 minus 5, what's 2 minus 5? Negative 3, which isn't in our domain. So you wrote a symbol there, you made so that we could put a symbol there that isn't in our domain. So you have to be careful with your operation symbols. You need to make sure that they are closed on your domain. That's the terminology for it. Closed on your domain means that anytime you give it 2 inputs from your domain, the output is also from your domain. I was going to have that conversation clear with the exercises, but glad we caught it early.
Just to verify, all inputs and outputs have to be within the domain. And there's not like this range domain difference.
Right, nothing about ranges here. All the outputs and inputs come from your domain. That's what it means for an operation to be closed on the domain. I can't do 5 plus 7 equals SpongeBob, have some operation that takes 5 and 7 and spits out SpongeBob, because SpongeBob isn't a real number.
So it's like defining all things that could be possible in the universe.
Right, so this has to be, your domain of individuals has to be your universe. It has to be everything that you could possibly be talking about. So if we replace n here now with z, this is now a valid interpretation. Z is the integers. So our domain of individuals is the integers, all the positive and negative full numbers. Now this is a perfectly valid interpretation.
Doesn't that
A
mean,
false interpretation, but an interpretation.
doesn't that mean the domain of mathematics has the word, the term undefined in the domain?
When we define the division symbol in arithmetic, we define it in a very careful way to keep it from allowing dividing by 0.
So we avoid that at all costs.
It's a problem that we address in the axiomatic system. It is not a problem of interpreting axiomatic systems.
I see. So it can never be the output of a valid mathematical axiom system.
Yes.
Gotcha.
Okay. But yes. There we go. All right, let's come up with an interpretation for this. There exists a y such that x plus y is greater than x. So there exists a y, and then tell me what to write.
What's the domain?
3.
Pick the domain. What should our domain be? Let's make our domain the number 1, 7, and pi. Perfectly valid domain. Don't think you have to be doing special things like all real numbers or whatever.
So what you're saying is the output could only be 1, 7, or pi?
Oh yeah, I better think more careful about that. We're in trouble. Good catch. We would get in trouble with how we define that operation symbol, keeping it that simple. We'd have to think real carefully. So we can keep it something like just real numbers. Keep it simple in this particular case. But there's nothing special. There's no reason you couldn't have a simple domain of objects if you wanted. But bad time to introduce it. Okay, continuing with here.
3.
3.
Plus y.
Well, let's not use plus again. Should we use times? We haven't done times yet. Times y.
Is greater than 3.
Well, we only have to do greater now. We're doing interpretation. equals 3, something like that. Replacing the symbols with new symbols defined on our domain. Now we could have, just to be perfectly clear, this was perfectly valid. You can reuse the same symbols if they're defined on your domain, and that's perfectly fine. You didn't have to replace them. Good? Okay. So, reading, I'm going to read this one more time and see if it all just clicks now and it sounds like I'm speaking pure English. No Latin. Sentence S is an interpretation of formula F. Here's sentence S, here's formula F. Sentence S is an interpretation of formula F with respect to the domain of individuals D, if and only if S can be obtained from D by substituting predicates and operation symbols defined on D for predicates and operation symbols in F, and by substituting constants in D for constants and free variables in F. That all makes sense? Oh, I guess we forgot to come up with the interpretation of this. Let's come up with the interpretation of this. Or I'll give you an interpretation of this, and this time I'll make the domain really simple. I'm going to make my domain 2, 6, 8, and I'm going to make my interpretation 2 plus 6 equals 4. Oh, I forgot my 4. 2, 4, 6, 8. So there's my domain of individuals. Here's my interpretation.
You could replace that with a minus.
Well, we'll pretend that 2 plus 6 is defined to be 8. Make sense? Good?
Yep.
Okay. So there's that. So we got interpretation. Now we need to move to universally valid. We talked about tautologies. From here on out, we're talking about things being universally valid. It's our counterpart to tautologies. What was a tautology? It was a sentence that was true under every sentential interpretation. What is it going to now mean for something to be universally valid? A formula is universally valid if and only if every interpretation of it in every non-empty domain is true. So every interpretation is true on every non-empty domain of individuals. So you don't get to pick D to be the empty set.
And that's the only thing.
That's what it means to be universally valid.
Right.
Okay. So intuitively, what this is giving us is tautologies. Some formula is a tautology if the sentential connectives alone make it always true. A formula is going to be universally valid if it's always true in virtue of all its logical form. So, if the sentential connectives alone make it true, then it's going to be universally valid, but it's also a tautology. If the sentential connectives alone don't make it true, but when you look at all of its logical structure, then it's always true, then it's universally valid.
Is it, okay, so
Draw a picture over here. Here's all your tautologies. Here's everything that's universally valid. Every tautology is universally valid. Not everything that's universally valid is a tautology. We are not only interested in tautologies, we are interested in things that are universally valid. Tautologies are things that you can always check with just a truth table. These are the things that you would have to check with a derivation. Maybe a truth table, that works, but maybe something beyond a truth table. Here was our example of something that's universally valid. You can't construct a truth table for that. There isn't a truth table where you can check all the x's. Because we don't know what all the x's are. In like manner, interpretation is a stricter notion than sentential interpretations. Sentential interpretations, we just have to replace sentences with sentences. In an interpretation, we have to replace predicates with predicates, operation symbols with operation symbols, quantifiers with quantifiers. We have to preserve all the structure when we create an interpretation. Every time we create an interpretation here, look at all the structure we had to preserve. Whereas when we came up with a sentential interpretation, the only thing we had to preserve was the high-level sentential connectives. Much weaker. So every interpretation is a sentential interpretation. The converse is not true. Every tautology is universally valid. The converse is not true. That picture helping like I hoped?
No. Intuitively, you think every tautology is a universal.
Every tautology is universally valid.
We'd love an
Excuse
example.
me, the other way around.
Everything that's universally valid is a tautology.
Yeah.
So here's our
That's how I
example.
interpreted the square. No, I understand. I'm just saying your picture. My intuition did not think like you.
Okay, here's a dot, represents a sentence. That sentence is universally valid. It is not a tautology. Here's a sentence, that's a tautology. It's also universally valid. This sentence is right here. This sentence is right here, where the R here now represents a full-blown sentence, not a predicate.
Mm-hmm.
This you can check with the truth table. This you cannot.
Yeah, but it seems like you should be able to.
The reason you can't is because you can't check all your X's there.
Wait, that's the only reason?
Well, that's part of it.
Oh.
Okay, we good?
It seems like always true by virtue of its logical form is saying the same thing as a tautology.
So with the tautology, it's like we just blindly look at the sentential connectives that are being used, big picture. So here's an example when we did this. So this is a sentence and a sentence implies a sentence.
Okay.
Looking at those sentential connectives alone, that is not a tautology. If you drew up the truth table for that, that is not always true. Yet when you replace A1 with that, you replace D2 with that, and you replace theorem 4 with that, now it's always true. But it's universally valid. Because you can't come up with a truth table for this thing.
In that form. With those.
Because it's not just replacing sentences with sentences now. Make sense?
Yeah.
Now, it could have been the case if I would have looked at, let me give you another one using the same thing. If I looked at axiom 1 or not axiom 1. Now, that is true just by looking at sentential connectives. I don't even need to look into what axiom 1 looks like anymore. So this one, the way that we validate that this is always true was looking at all its logical structure. This one, just by looking at its top-level sentential connectives, the things connecting sentences together, we could already determine it was always true. So this one is a tautology. It's also universally valid, but it's a tautology. It's a stronger notion.
But
This one is not a tautology, but it is universally valid.
But didn't you go through the exercise of explaining why the top one is a tautology? Because regardless of the true or falsity of the left-hand side, the implication makes it always true.
No, I said, when you come up with an interpretation that makes A1 true and makes D1 true, so whatever that interpretation is, if it made both these things true, then that interpretation is also going to make this thing true.
Right.
That was an interpretation. That wasn't just a row on a truth table. How many interpretations could we make of this thing?
Oh,
Infinitely many. And they're all could be significantly different from each other in what they say.
so it's,
With the truth table, there's only two things to check. Is it true or is it false?
so it is dependent on whether or not A1 is true. We do care what the truth value of A1 is.
In this scenario, yes.
Okay,
But we care about more than just the truth or falsity of...
right.
Right, we cared about its logical structure. In order for me to know that these things imply this is always true, I'd have to know what those things actually are.
Right.
Here, you don't have to tell me anything about A1.
Right.
And it's always true.
Okay, so the universally valid is saying here every non-empty domain. Is this saying every single non-empty domain that has ever existed?
Yes.
So if
Pick any crazy interpretation of this sentence you want, this sentence you want, and this sentence you want. Now, they're all in the same system, so whatever you replace Q with here, you have to replace it with here, you have to replace it with down here. Because you're interpreting this whole thing all in one go. But any interpretation you come up with, across any crazy domain of individuals you can come up with. Stay up all night coming up with all the crazy stuff you want, plug it in here, you're going to see one of two things happens. Either your interpretation made one of these two things false, or it made this thing true. And if it made these false, the whole thing's true. Or if you made this true, then you also made that true, and the whole thing's true.
But if theorem 4 is false,
So is it fundamentally?
If you came up with an interpretation that made these things true, then this is also going to be true in that interpretation.
right, but if theorem 4 is true, and the left-hand side is false, then it's false.
That's true.
False implies anything is true.
Oh, it's the true.
It's vacuously true. So the only case we actually care about is if these are true, is this also true? That's all we ever check in practice.
Right.
Because if these are false, who cares?
Okay, so just if we replaced A1 and D2 in theorem 4 with the formulas,
With these formulas.
could
do,
we then
do.
turn it into tautology at that point?
No. It's not a tautology.
Ever? Like no matter
It's
how you
never a
structure it?
tautology. A tautology, the only way it can be a tautology is if these things alone were making it always true. The sentential connectives alone were making it always true.
Okay.
And it's not the sentential connectives alone that's making it always true. It has to do with the predicates and the quantifiers and all the logical structure that we extract. We have to use our full-blown grammar. We don't just get to use parentheses and sentential connectives and letters to symbolize sentences in our merry way. So, another way to think about it is tautologies are what we talk about when we're just in propositional logic. Once we get to predicate logic, we now care about things being universally valid. Another way to think about it. Good. Any other questions? This is good. Get this all clear. This is like the next big lecture. Once you get this one, it's smooth sailing after this. Dumping all this terminology on you.
Good thing I'll forget it next week.
Well, I'll record it just for you. You can rewatch it before next week. If it takes a week to forget, or even just a day. Any other questions before I move the camera? All right. Let's move the camera and have this conversation about why a non-empty domain. Okay, I still got that. So this is still on the camera. Okay, so far you might have been okay with this, except for this part might be annoying you a little bit. Why a non-empty domain? Why can't we have an empty domain? Now, it's not really that we can't have an empty domain. It's that we don't care about empty domains. These are setting up fields of study of things. We never care about the field of study of nothing.
Why do we even have to say that?
Well, just to make sure you don't use an empty domain. Now, when we have a non-empty domain, then there's going to be some nice things that we get that we don't get on an empty domain. So one reason we don't want empty domains is because we just don't care about things that have empty domains. We're not studying nothing. We're not studying the operation symbols and predicates that we can apply to nothing. We don't care. So that's just high level why we want it. But now we get two nice things when we have a non-empty domain. So here is a piece of thinking that is only true if your domain is non-empty. We can go from saying, if it's true that for everything in our domain, it's a P. So if we know that for all x, P of x, then we can conclude that there exists an x such that P of x. If I know that all numbers are prime, then I know that there exists a prime number. And that's a piece of thinking we want to use over and over again in our systems. This thinking only holds in non-empty domains. If we were on some empty domain, well, then it's true that everything in there P applies to. That is true. But it is not true that there exists something in there that P applies to, because it's empty.
So all could be nothing, but exists can't be nothing.
Right. And so, our domain of interpretation will always be some non-empty set, and that's all we care about, are non-empty sets. So this will be a piece of thinking that we use throughout the rest of the course, and it's perfectly valid. The other reason we like it is we like to think of these two things as being contrary to each other. We like to think about these as being inconsistent. If for all x, P of x, then we do not want it to be the case that for all x, not P of x. In other words, we want this to always be a bad statement. For all x, P of x, and not P of x. We never want to be able to say something like that. We could say that on an empty domain. Is it true that everything in there P of x applies to? Yeah. Is it true that everything in there not P of x applies to? Yeah. And so, on a non-empty domain, that's no longer the case. If there's at least one thing in there, then it has to be this or it has to be this. Can't be both ways. And so we can use this when we're trying to do proof by contradiction. We can consider this a valid contradiction. Does that make sense?
Mm-hmm.
And then this right here is just a definition of that. So this says the same thing as that, but just another way we think about it. We want to think for all x, P of x is a contradiction of there does not exist an x such that P of x. If I say all numbers are prime, we want that to contradict that there doesn't even exist a prime number. We want those to be contrary statements. Make sense? So these are pieces of logic that are not true on empty domains. They are true on non-empty domains, and we will use them. Make sense?
My dyslexia kicked in for a second. I reversed listed statements. You gotta say it again.
I got to say it again.
What you just said.
Not sure what I just said. These statements are true when our domain of interpretation is not empty.
Right.
If our domain of interpretation is empty, then these are now invalid pieces of thinking. So we're going to deal with non-empty domains. So I'll read it one more time. A formula S is universally valid if and only if every interpretation of it on every non-empty domain is true. That's what we mean by universally valid. Okay. What do we typically use interpretations for? Some ideas that we already talked about back in chapter 2 when we only had these types of sentences. So similar idea. Similar to how we use sentential interpretation, we use interpretation. So we use interpretations to prove, one, that an argument is invalid. How do we show that an argument is invalid? We come up with some interpretation that makes the premises true and the conclusion false. Back in chapter 2, we said to show an argument is invalid. We come up with a sentential interpretation that makes the premises true and the conclusion false. Now we say to show an argument is invalid, we come up with just an interpretation that makes the premises true and the conclusion false. We often call that a counterexample. I say something like, every prime number is odd. So what am I saying? I'm saying if it's prime, I'm saying prime implies odd. There's my false statement. How would you prove that this is invalid? I say if it's prime, then it's odd. You say 2 is prime and it's not odd. 2 satisfies the antecedent, the premise, but it shows the conclusion is false. So how do you show an argument is invalid? You come up with the interpretation where the premises are true, but the conclusion is false. It's often called a counterexample. Second thing we often use them for is for that showing that premises are consistent. What did it mean for premises to be consistent over there?
The sentential connected stayed the same, right?
No. So some premises were consistent over there if there was some sentential connective that made all the premises true. Mm-hmm. If it was possible for them all together to be true. So you wrote out your truth table, and if a truth showed up even once, then the premises were consistent. They could altogether be true. Now, how do we show that premises are consistent here? We show there is some interpretation out there that makes them all true. Give you an example. Your parent says, "Where were you last night?" You said, "I was doing homework at Bill's house." Your parent asked Bill, "Where was my child last night?" He says, "Oh, we went over to Jack's to play video games." Those two premises are inconsistent. One of you is for sure lying. Now your friend could say, "Oh, he came over and we did homework last night." They could still be lying, but now at least your premises are consistent. So consistent premises doesn't mean that they're true. It just means it's possible for them to be true. If your premises are inconsistent, we are guaranteed at least one of them is false. Make sense?
Mm-hmm.
And then the last thing we use interpretation for, and a very common use case for it, is to show that axioms are independent of each other. When we set up an axiomatic system, we do not want to introduce as an axiom something that could have been proved from the axioms. So if I have some axiomatic system, A1, A2, and I introduce another axiom, A3, if A3 could have been proven from A1 and A2, I don't want it as an axiom. And I want that to just be a theorem in our system. Right?
Mm-hmm.
So how do we prove that axiom 3 needs to be an axiom? How do I show I can't prove it from axiom 1 and axiom 2? I would show that the argument A1 and A2 implies A3 is invalid. If this is an invalid argument, then I cannot use A1 and A2 to prove A3. If I can come up with some interpretation where A1 is true and A2 is true, but A3 is false, then the axioms must be independent of each other. Because if A3 was really dependent upon A1 and A2, then any interpretation that would make A1 and A2 true would also make A3 true. So if I can come up with some interpretation that makes those true and that false, then the axioms are independent of each other. And that's how we check, do we have too many axioms in our system? You can actually go through the process of checking. Any questions on that? So, with that giving you the intuition, let's give the precise definition of what these things mean. So what does it mean for an argument to be invalid? I just was giving you high-level notions of what it meant. So an argument is invalid if and only if it has an interpretation, at least one, it has an interpretation on some non-empty domain that makes the premises true and the conclusion false. Typically called a counterexample. That's what it means for an argument to be invalid. If there's at least one interpretation out there on some non-empty domain that makes the premises true and the conclusions false, then it's an invalid argument. Similarly, what does it mean to say that a formula is consistent? A formula, typically the formula we care about is fancy P. What does fancy P stand for? The conjunction of all our premises. So over here, in weak preference, fancy P stood for A1 and A2 and D1 and D2 all ANDed together. So it's a conjunction of all our premises. That's usually what we care about being consistent. So a formula, typically the one we care about is a conjunction of all our premises, is consistent if and only if it has at least one true interpretation on some non-empty domain. Good? Pretty straightforward definitions. Okay, so with that, let's prove an argument is invalid. So starting with this. Some men are liars, Adam is a man, therefore Adam is a liar. We're going to prove this argument's invalid. First thing we're going to do is symbolize the argument. So tell me what to write for this.
There exists. Wait. Interaction with domains. How do we?
Well, so far we're going to symbolize it, and then we'll come up with our interpretation. So first, just symbolize.
There exists man such that
X is a man.
X is.
So it's that
No,
manness
liar.
applies to X,
Oh, and liar applies.
and liar applies to X. Okay, there's our first one. What's our second premise?
Just X.
M applies to Adam.
So tell me what to write.
There exists
There exists X.
such that.
Or no, it's A, right?
Such that, what?
Ax.
Such that being Adam applies to X?
Oh, okay.
It's
No,
just saying
M
there
applies
exists
to
an X.
Adam.
Well,
Just M applies to Adam. Just MA. Remember, Adam is a constant. So this right here is how we symbolize the sentence. We only need to apply quantifiers to free variables. This just says Adam's a man, where manness applies to Adam. Perfectly valid. Okay, and what we're trying to prove is that being a liar applies to Adam. Now, how do we show that this argument is invalid? We come up with some interpretation that makes our premises true and our conclusion false. So first, let's pick our domain of individuals. It's very standard to just use arithmetic because we can reason very well about algebra that we've been learning since we were in grade school, right? So that's a pretty standard one. So we can pick our domain to just be the real numbers, and that way we can just use things on the real numbers that we don't know. So we would symbolize this as there exists x such that, give me something we can say about numbers. What's a property a number could have?
Can be odd.
Odd, such that oddness applies to x. And what's another property a number can have?
Even.
Even applies to x. But there isn't a number that's both odd and even, so you need to pick something, a property an odd number can have.
Negative.
Huh? Prime. So there exists x out there such that x is odd and prime. That's our interpretation. Next, tell me a number that's odd, but not prime.
21.
21. There's a lot of them out there. Oddness applies to 21. Most of the odd you would have picked, I guess early odd numbers are for the most part prime, so I guess the hesitation kind of makes sense. And therefore, prime applies to 21. Is 21 prime?
No.
It's 3 times 7, so no. Is it odd?
Yes.
Is it true that there exist numbers out there that are both odd and prime?
Yeah.
Yes. So we came up with the interpretation that makes the premises true and the conclusion false. So this is for sure an invalid argument.
Could you have still done that with the first argument? Just like, what domain would you use?
All the people.
So you kind of wanted to think that this has a domain embedded into it.
Men, right?
That's where my mind went, is we had to prove it on that domain.
So you could have used the domain that your intuition told you that this was talking about,
Which is all men, right?
which is men. You could have if you wanted to. We already were given a sentence that intuitively you can pretty much to see, yeah, obviously that's false. But the point here is to show you the process. Some sentences are obvious that they're false. Other ones, I could give you more complicated sentences where it's hard to tell, wait, is that a valid argument, yes or no? And then converting it to arithmetic, where it's much easier for you to tell valid versus invalid arguments, makes it easier for you to classify correctly. So that's just a process, but I see how you can just see it from reading the sentence directly. Okay. Next example, A1, A2, D1, and D2, all over there, are consistent. How do we show that they're consistent?
They can all be true.
We come up with an interpretation such that all 4 of them are true. And I intentionally made sure, when it was all said and done, all the interpretations we had written down were true. So, you'll notice I replaced all our Q's with less than or equals. So I was consistent. I replaced all our I's with equals, and I replaced all our P's with less than's. And so all the sentences that we have written out here are true. Is it true that for all x, all y, and all z, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z? If I know that x is less than or equal to y, and I know that y is less than or equal to z, what do I know? X is less than or equal to z. That was our interpretation of axiom 1. For all x, for all y, and for all z, if x is less than or equal to y and y is less than or equal to z, x is less than or equal to z. So our interpretation of A1 was true. What was our interpretation of A2? It says for all x and all y, either x is less than or equal to y or y is less than or equal to x. Sorry, I erased those. Put those back. There's our interpretation for that. What was our interpretation for D1? D1 was just a definition, so it can't really be false. Oh, no, it could be. Is it true that x is equal to y if and only if x is less than or equal to y and y is less than or equal to x? Yes. If I know x is less than or equal to y and y is less than or equal to x, what do I know? They're the same number. Or in other words, they're equal. And then finally, is it true that if x is less than y, then y is not less than or equal to? Oh, no, that was a theorem. D2. D2. X is less than y if and only if y is not less than or equal to x. If y is not less than or equal to x, y must have been greater than x. If y is not less than x and y is not equal to x, y is greater than x. Right? So we gave an interpretation of A1, A2, D1, and D2 that were all true. Since we could find some interpretation that made all 4 of those true, then they're consistent.
So wouldn't that mean that the some men are liars formula, whatever, that could also be consistent?
Right, that's.
Yes, some men are liars and Adam is a man. Those are consistent premises. It is possible for some men to be liars and for Adam to be a man.
And
That is
also
perfectly possible.
Adam to be a liar.
Yes,
It's possible
could've-
that a sinner, yeah.
we could've.
And it could have also been, Adam could have been also a liar. It was possible for it to be true.
So that would make it
These 3 sentences together are all consistent. This, and this are consistent. It is possible to come up with an interpretation where all 3 of those are true.
So
we
what
found
were
an
we trying to
interpretation where it was false.
We
It's
showed
not universal.
that it is not universally valid. It is not always the case that if some men are liars and if Adam is a man, then Adam is a liar. That is not universally valid. There are cases where it's not true. Consistent means that there are cases where it is true. That's what consistent means. Universally valid means there are no cases where it's not true.
Right, okay.
Consistent means there's at least one true case. Universally valid means they're all true cases.
It's kind of like the output of, okay, no, yeah. It's what was the opposite of tautology?
You know I hate that word.
I know. It just triggered my brain. I'm like, damn it, I used the word.
Contradiction.
Yeah.
The opposite of a tautology, if you force me to say one, is a contradiction.
I'll just have to think about it.
Standard contradiction is A and not A. Truth table is always false. It is the opposite of the truth table being always true.
I'm trying to think if somehow consistent and universally valid are contradiction.
No.
They're not.
Consistent means it could be universally valid.
But it's
Inconsistent, for sure, well, inconsistent doesn't affect it being universally valid. We should be careful about that.
so
Let's pretend that A1 and D2 here were inconsistent. Let me rewrite it over here so we're on camera. Go back. If I know that A1 and D2 implies theorem 4, let's say I know that this is universally valid. That does not necessarily mean that these 2 are consistent. Maybe they're inconsistent. Maybe my premises are always false.
okay, so
False implies anything is
True.
true. It's why we can never allow, in our axiomatic systems, we never allow them to ever become inconsistent. Because the second they become inconsistent, everything's provable.
Yeah.
Because false implies anything is true.
would it be fair to say that consistent could be a box wrapping around universally valid tautologies? Like
No.
all things consist.
These 4 right here could be inconsistent. Or those 3 sentences could be inconsistent. And yet it could be universally valid.
Oh.
If this is inconsistent with this, let me give you an example. Give you something that's universally valid. Here's one that's universally valid. If I take A1 and not A1 implies theorem 4. Plugging in with exactly what we have over there. Universally valid with inconsistent premises. Because this is always false. False implies anything is true. Your system becomes useless the second that you allow an inconsistency in your premises.
Okay.
If we allow one contradiction into any system, we can now prove everything. Because we get the false side on there. Sometimes constructively, you might remember the proof that I'm the Pope.
Yeah.
Okay, good. Lots of clearing stuff up. Any other questions so far? So we did that. Okay, how to show premises are not consistent. Another way that we can show premises are inconsistent. So this is how we check if premises are consistent. How do we check if premises are consistent? Come up with an interpretation where they're all true. It could be the case that every interpretation you're coming up with keeps making so that they're not all true. You might wonder, maybe they're inconsistent.
If you can't come up with an example being true.
But maybe we're just not very smart and we can't think up the example. So maybe they are consistent, but we're stupid. And we can't think up that one clever case that makes them all true. So how can we actually check that premises are inconsistent? The way that we can show premises are inconsistent, same way we did it before back in chapter 2, is we show they imply a contradiction. If my premises imply a contradiction, then they're also inconsistent. We did some examples with that. We took some inconsistent premises, we drove a contradiction, therefore we knew our premises can't altogether be true. Because if they were altogether true, then my conclusion would have to be true. But my conclusion was for sure false, therefore one of my premises has to be false. So I have inconsistent premises. That's how you show inconsistent premises. Okay, next one. Let's show A1 and A2 are independent over there in our axiomatic system. How do I know that I secretly couldn't somehow prove A2 from A1? Well, we can try a whole bunch of times, and we might have read it, got suspicious, and said, I think maybe I can prove A2 from A1. And so we stay up all night working on it, and we're getting nowhere. And so we wonder, is this even possible? Let's show it's impossible. So how do I show that you can't prove axiom 2 from axiom 1? I show that A1 implies A2 is impossible. It's an invalid argument. How do I show A1 implies A2 is impossible? I need to come up with some interpretation that makes A1 true and makes A2 false. And if I can do that, then A1 obviously doesn't imply A2. It's not going to be the case that every time A1 is true, A2 is also true. So they're independent axioms. A2 actually gives us new information. It isn't somehow just giving us the same information A1 does. If A2 secretly just gave us the same information as A1, then anytime A1 was true, A2 would also be true. So let's do it. Let's come up with an interpretation for A1. Does it start with 3 quantifiers? Yes. Okay, so for all x, for all y, for all z, let's come up with our interpretation. What should I use for Q? We want to make A1 true, but A2 false. So I need something that I can plug there such that this is transitive property, right? So I need something that has a transitive property but isn't reflexive, or symmetric, I mean.
Less than or equal to y.
Less than or equal to will be a true interpretation.
Oh.
Less than or equal, if it makes this true, it will also make that true. That's the interpretation we use there. So we want to come up with an interpretation that makes A1 true but A2 false.
Less than?
Just less than. So x less than y and y less than z implies x is less than z. Is that true?
No.
If I know that x is less than y and y is less than z, do I know x is less than z?
Yes. Yes.
So it's transitive. Going back to discrete math. Those 5 properties on a relation. Reflexive, symmetric, transitive. It's transitive, but it's not symmetric. So for all x and for all y, oh, wait. This has nothing to do with symmetric, but your interpretation still works. X less than y or y less than x. Is it true that for any 2 numbers you choose, you either have x is less than y or y is less than x? No, the special case is when you choose the same number twice. So there we go. We came up with the interpretation where A1 was true, but A2 was false. Therefore, they are independent axioms. It actually gives us new information. And so you might wonder, going back to like your geometry class, if you're currently in geometry, do we actually need all those axioms that were given? And how do we know that we actually need all those axioms? This is exactly how you ensure that you don't have extra axioms. You might be suspicious. Could I prove axiom 17 from these other ones?
Don't we have an extra axiom in our book?
There are some things that we introduce as axioms that we specifically say, this could have been proved, but the proof is a pain, so we're going to accept it as an axiom. But it's really a proof. We mark it as a theorem in our book, so the book doesn't lie. We don't call it a postulate. We say, here's theorem 17 or whatever it is. And we say, we're not going to prove it. It could be proved. We're going to treat it like a postulate, but it's not really a postulate, it's a theorem. So nothing's mislabeled in the book. But yeah, we occasionally do that. Any other questions? All right, let's move it again. We're going to start on the far side of the board and then go off on a tangent. A fun tangent, but tangent. Hopefully I can get the whole board. I'm going to have to shove that an inch. Okay, got the whole board. All right, so now we're looking over here. And over here, we're just going to do some examples to help cement this in. These are just exercises out of the book. All right. We're going to show that the following are not universally valid. So A, we need to show that this is not universally valid. How do we show it's not universally valid? We need to come up with one false interpretation of it. If we can come up with a single interpretation of this on some non-empty domain that makes it false, it's not universally valid. So what should we pick our domain to be?
Real numbers.
Real numbers, okay, that's a good one. So we'll say our domain is real numbers. Now let's come up with our interpretation. So for all x, give me some property real numbers have.
Even.
Even. If even applies to x, and give me another property that even numbers can have.
Divisible by 2.
That is what they
Is it there?
We'll do prime. Prime applies to x. Implies, what's a property that 2 does not have?
It's not odd.
Odd. Okay. Is it true that for all x, if it's even and it's prime, then it's odd? No. 2. 2 is even. 2 is prime. Is 2 odd? No. So there we go. We came up with the interpretation that made that false. And we could have picked a bunch of random interpretations, and most times it probably would come out false. Well, maybe not, because we have to be careful to make sure the antecedent can be satisfied. Okay, so there we go. Not universally valid, came up with an interpretation that makes it false. This one, for all x, x is greater than or equal to x. Trick question, this one is universally valid, right? It is always the case that x is greater than or equal to x. So this is universally valid.
On what domain?
we're showing the domain of real numbers, right?
Ah, okay, we'll say our domain is real numbers.
That is true.
Yeah, but is every interpretation of it true? No, this isn't universally valid.
Huh.
All right, let's come up with an interpretation. So we picked real numbers. For all x, give me some operation, or give me some relation on the real numbers.
Less than.
Less than. There's an interpretation of that. This interpretation happened to always be true on the real numbers. That does not make it universally valid. Okay. Universally valid means under every interpretation you can come up with, on every non-empty domain, it's true. Here's an interpretation on a non-empty domain that makes it false. So it's not universally valid. Don't read too much into it. All right, let's try another one. There exists an x such that h of x or not a of x. What should we make our domain?
Real numbers.
So we'll make our domain the real numbers again. So there exists x such that, pick some property a number could have. Prime. Prime can apply to x. Or, now what's something that's impossible for it to be if it's
Not rational.
not rational. Okay, so let me think. We want, we're coming up with an interpretation that makes it false. So there exists a number that, that's an or, not an and. So we need to state two things that's impossible for our number to have. Okay. I'm going to help you with this one to see how restricting your domain could help. Okay, so I'm going to make my domain of individuals equal to the number containing 1. There's my domain of individuals. Now there exists an X such that I'm going to make H here is the greater than 1 property. Such that X is greater than 1, or it is not the case that, what should I make for A? I'm going to do the is even property, or is odd property. Okay, there exists something in our domain such that it's greater than 1, or it's not odd. False. That thing is greater than 1, and it is odd. Now, the author gave that to you because if you were to do this on some domain like all the real numbers, you would have gotten stuck for a while. Like, I can't come up with anything.
Makes you feel like there's hardly anything that's universally valid.
Universally valid is not a trivial property. And we usually need a derivation to demonstrate that it is universally valid. But just looking at it, you could have guessed that, does that always have to be the case, whatever that is? No, why would it? Nothing compelling about that. So hopefully your intuition was saying, for sure that's not universally valid. Just kind of hard to think up an interpretation that shows that it's not universally valid. Okay, next one. Show this and this are consistent. So we're trying to show that these two premises are consistent. It's possible for this to be true and this to be true. Okay,
It just has to have one true interpretation.
we're now just going to replace the things right below, and I'm not going to bother rewriting out the whole sentence. So, what is a domain that we could use?
Natural numbers?
Domain equal to what? Naturals, you said? Oops. I just need to write the rails. Okay, if the domain is natural numbers, let's see. There exists an X such that for all Y, X, Q, Y. What could be our relation symbol there?
Less than?
There exists an X. Okay, that works. We could do X less than Y. There exists a natural number that's less than every other natural number, right? Almost, if you do less than or equal to, because Y could be the same as X. So now that would work for that. Let's look at this one. For all X and for all Y, there exists a Z such that X less than or equal to Z and Z less than or equal to Y. Is it true that for any two X's and Y's you choose, you can always find the Z such that Z is greater than or equal to X and Z is less than or equal to Y?
No.
Now, X here could be 9, and Y here could be 4. What's the Z that's greater than 9 and less than or equal to 4? There's one. So this less than or equal to interpretation does not work for Q on this domain. So we either got to pick a different operation symbol or a different domain. Any other ideas?
Equal?
Yeah, equal.
Equal. Okay, so let's try the equal. Domain still naturals?
Mm-hmm.
Okay. For there exists an X such that for all Y, X equals Y.
Yeah.
There is some X that's equal to every other Y. Okay, so there goes that idea.
Are we, do we want to get into domains that aren't numbers?
You can get into domains that are whatever you want. Numbers are usually easy to work with.
Or would you recommend?
I'll help you out. What I do when I start getting stuck is I start saying, let's mess with just a simple domain to see if that helps me. Let's make our domain 1. Okay, now what should we try?
Oh, well that would work. Equals.
Equals. Here's our only domain. Is it true that there exists something in our domain such that for everything else in our domain they're equal?
Mm-hmm.
Yes. Is it true that for everything in here and for any other thing in here, we can find something in here such that that's equal to that and that's equal to that? Yeah. Okay, there you go. There's our interpretation. So coming up with these interpretations can be kind of tricky. Next one. All unicorns are animals and no unicorns are animals. Let's show those are consistent.
They're contradictions.
Exactly. It sounds like they're contradictions. How on earth could these two things be consistent? Now we'll remember that these are not contradictions. What's the contradiction of all unicorns are animals? Some unicorns are not animals.
That's not a gate. Same.
That's right.
So let's symbolize this really quick. What does it say?
For all x, unicorn applies to it.
For all x, unicorn applies to it?
Yeah. Well, I mean, thanks.
That says all unicorns are animals?
No. For all x, where x is a unicorn, animal applies to it.
Yeah, if it's a unicorn, then it's an animal. There's our symbolization. And our symbolization for this is for all x. How do we symbolize this one? No unicorns are animals.
If it's a unicorn, it's not an animal.
If it's a unicorn, then it is not an animal. Okay. What can our domain of interpretation be?
Real animals.
Real animals. Let's say D equal to the actual animals domain. And now it's true that for all animals, if it's a unicorn, it's an animal. It's vacuously true.
Yeah. Sure.
Because no animal is a unicorn. And it's also the case for all animals, if it's a unicorn, that's not an animal.
It's because unicorns don't exist.
Because unicorns are not animals. They don't exist in our domain.
Just force it with the domain.
We picked something in our domain that this definitely didn't apply to, so they were always vacuously true. Good?
Is there a domain that we could do that, like, would make it, the
Oh, fantasy animals?
antecedent
It would make
true?
it.
Sure. You could have made a D just all imaginary creatures.
Yeah.
And then, however we define unicorn, have to define it in a way that's an animal, I guess.
Thanks, Sonny.
Yep. Okay. One more. This one we don't need to do because we already had this conversation. This was going to be the one that I did to remind us that you can't let your operation symbols take you outside the domain. So that's what that one was for. We'll stop with that and now have go into the side conversation. So our side conversation here is going to be about checking if a statement is universally valid. See, when we were only talking about tautologies, we had a procedure, tedious as it was, to check if something was a tautology. When we were going back and looking at sentences like these, big sentences, no matter how big, scary, and hairy they were, you could always go through some procedure to check whether or not it's a tautology. Right? Does that make sense?
Mm-hmm.
Now the question is, could we do something similar for checking if some theorem is universally valid? Or if some statement is universally valid? Some statement like A1 and D1 applies or implies theorem 2. Is there some procedure we could use for determining if it's universally valid? And some idea you might have is, let's just check all the possible proofs we can construct. So you might think, I can start a proof by just starting with my first axiom. And check, does that prove theorem 2? No. Okay, what if I started with axiom 2? Does that prove theorem 2? No. What if I start with definition 1? What if I start with definition 2? Okay, no. Well, maybe if I start with axiom 1 and apply to axiom 1 again. Does that get me to theorem 2? No. Well, what about if I did that or that and then that? And then go through all the possible ways that we could do 2 steps of thinking, and then 3 steps of thinking, and 4 steps of thinking, and 5 steps of thinking. And checking, ultimately, doesn't give me the end result I'm looking for. Writing out line by line of your proof. Right? Just check all the ways I can keep writing out the next sentence in my proof. Is there some procedure, some formula, some general way of producing these things? Could I write some algorithm on a computer, some procedure that just goes through and manually checks all the possible next steps we could have taken, and just keep going until we find out, oh, we got theorem 2. That's what we were looking for. Is it possible to do that? Now, it would make sense that it appeals to your intuition that you should be able to do that, because that was the intuition of great minds in the early 1900s. But the answer is no. and provably no. So there is no general procedure for proving that some statement is some formula like this is universally valid. You cannot go give me some formula as a general rule and write some program that checks, is that formula universally valid, yes or no? In other words, there is no formula for generating proofs of statements. And provably so. In first order logic, every system of mathematics uses first order logic. So since there's no proofs of universally valid statements in first order logic, by extension, there's no proofs of universally valid, there's no generic formula for generating proofs of universally valid statements in any system of mathematics, because they all presuppose first order logic. So it's not even possible in first order logic. Forget all those other systems. That was proved by Alonzo Church. He demonstrated that that problem was undecidable. Those of you from computation theory, you might remember that beautiful word, undecidable. I'm going to give you an idea, a basic idea of what this undecidability means, and remind you of something that we talked about called the halting problem. Those of you who didn't do computation theory, that's okay. The halting problem is just a simple logic problem. This isn't how he proved it, but it gets at the idea of the thinking he used in his proof, in showing that something is undecidable. So, the halting problem, what's the halting problem? Imagine that I built some magic computer. My magic computer, H here, has the ability that you give it any blueprint for some other computer, and the input that you're going to run on that computer, and my computer is going to tell you one of two things. Yes, it will run that blueprint, and the program will finish executing, or no, it will never halt. It will somehow get in an infinite loop. Something like that. So H here is a magic computer. You give it the blueprint to a blueprint of a computer is the same thing as running a program. I know you don't think about it that way, but that's what it is. When you execute Microsoft Word on your computer, you're having your computer simulate another computer. That's what's happening. Every application, every program is just simulating a computer.
Blueprint is code, isn't it?
Blueprint is code. Yes. So you give a blueprint and an input, and this magical program, this magical computer, can tell us, yes, this blueprint will accept that input and it will never crash. Yes, it will accept the input and it will eventually stop. It will finish some computation. So some blueprint and some input to run on that blueprint. Yes, it will eventually finish the computation, or no, it won't. It will go off forever and it will never finish the computation, whatever you told it to do. That's what H does. Magical computer, we're going to show that this is an undecidable problem. We're going to show that it is impossible for such an H to exist. There will never be some computer out there that if you give it some input, or some blueprint and some input to run on that blueprint, then in general it can tell you whether or not it will run that input correctly, or if it will go off on an infinite loop and never finish running the program. So we're going to prove H is impossible. Here's how we are going to prove it. We're going to construct a new machine M. And we add on this negation component. So M takes a blueprint and an input, it runs it through H, and then it runs it through our negator. Our negator just says, if H spits out true, we spit out false. And if H spit out false, we spit out true. You with me? Mm-hmm. So that's what M does. M just does the negation of H. H says, given that blueprint and that input, will it eventually finish the computation? Yes or no? Yes, it will finish. No, it won't. M just negates whatever H does. Now the question is it possible for this H to exist? Let's pretend that this H existed. And now we're going to have it run the blueprint for M. M is what we're going to feed into H. And we're going to just run some input. You with me? Mm-hmm. Now, one of two things is going to happen. H thinks it's going to halt, or it thinks it's going to run forever. Mm-hmm. So let's pretend that H says, which one should we handle first?
Halt.
Let's say H spits out a true, it halts. So let's pretend that on this input, H says it's true. Mm-hmm. Well then up here, on that blueprint, on that input, running M is our input here. Mm-hmm. We said H spits out true, but if H spits out true, what does M spit out?
False.
False. And so, H was wrong. On input M, if you said it was true, it actually spit out false. You lied to me, H. So maybe H says, oh, sorry, I meant false. Well, run it again. H says M will spit out false. Let's run through it. We get the blueprint and M. H says M will spit out false, and ends up spitting out true. So if H says M spits out true, M actually spits out false. And if H says M spits out false, it actually spits out true. No such H can exist. It's impossible for this machine to exist. And here's a quick little proof. And so in general, knowing whether or not a computer will be able to handle some input is what we call an undecidable problem. Provably, there is no machine, no algorithm. Give that thing, make this thing a supercomputer the size of our observable universe running the craziest AI that we've come up with now. Doesn't matter. That machine can't exist. It's not a matter of, it's really, really hard. It's not a matter of, well, with future technology, one day maybe. No, it's logically impossible. That's what we mean by it's undecidable. And in like manner, when Alonzo Church showed that we can never have some procedure that generates proofs for us in all these systems, it's not that it was really, really, really hard, and maybe one day with the right technology, it was, no, it's impossible. It's a logical contradiction to have such a procedure. The same way that H here can't exist. This is a standard example we use of an undecidable problem, which is why I'm using it. Plus, we did computation theory not so long ago, so good throwback for some of you. That make sense? Mm-hmm. So I know I'm not giving you the proof for how he did it. That's too much. But give you a taste for the type of thinking the proof involves. Mm-hmm. And we get into very messy situations where we have self-reference. The reason we talk about this with machines, what Alan Turing did in his famous paper, Alan Turing, the father of computer science, is he told us how to build a Turing machine that can simulate a Turing machine. And that's what all our Turing machines do now. Turing machine is just a computer. A computer, what do? You have it run some software. That software is basically just another computer. Alan Turing is the one that showed us how to, from a Turing machine, build one that could run any other Turing machine. We call it a universal Turing machine. And all computers are now built on that model. A Turing machine comes, and you can just run the code for this thing over here, or run the code for that thing over there. Mm-hmm. Prior to Alan Turing, if you built a machine to do something, if I built a machine to do arithmetic by running through cranks and all sorts of stuff, there's no reason that that machine that was designed to do arithmetic could suddenly go and solve some other type of problem. Run Microsoft Word. How on earth can this thing go from doing algebra to running a word processor without me changing any of the hardware? Mm-hmm. Why doesn't it just know how to do all that? And Alan Turing showed us how. How to get a Turing machine to simulate a Turing machine. That was the big breakthrough in computer science. And suddenly, look at where we are less than 100 years later. Mm-hmm. So, self-reference, very interesting things start happening. Let's give you another taste for self-reference. This statement is not true. Question, is that true? This statement is not true. True or false? Well, if it's true that it's not true, then it's
False.
false. So I say this statement is not true. You say false. Well, if it's false that it's not true, what is it?
It's true.
True. So if it's true, then it's false. If it's false, then it's true. So question, here's our statement, here's our proposition. Is it true or false? Every statement has to be true or false. Which one is this? It's not a statement. We just called it a statement. That doesn't magically make it so. We don't get to decide what these things are. They are what they are. And we can identify them correctly, and we can identify them incorrectly. Your feelings about whether or not that is a statement is completely irrelevant. Either it is or it isn't. Another place where we got in trouble in the early 1900s was considering the set of all sets that don't contain themselves. So let S be the set of all sets that don't contain themselves. This is a famous one referred to as, how did I lose his name? Russell's paradox.
Oh, yeah.
The question is S in S? Does S contain itself? S is a set of all sets that don't contain themselves. Does S contain itself? Let's say no, S does not contain itself.
Then yes.
But S is a set of all sets that don't contain themselves, so S contains itself. Alright, so let's say S contains itself. Well, if S contains itself, and it's a set of all sets that don't contain themselves, then S doesn't contain itself. And so the conclusion is,
It's not a set.
S is not a set. And this big breakthrough made us have to, it forced us to restart set theory and be far more careful.
Yeah.
Because we were being, those of you who have gone through it with me before, we talked about naive set theory. Naive set theory is a set theory that allows you to talk about this nonsense.
Is it, so the fundamental problem here is just the self-referencing, and the reason why the halting problem even exists is because of self-referencing. If you were to somehow remove the ability for self-reference, could we solve the halting problem?
Well,
If you remove the ability for self-reference, you no longer have a Turing machine. And so you're probably back down to like a push-down automaton. And that is fundamentally different from a Turing machine. And there are, the language we use in computation theory is, there are languages a Turing machine can recognize that a push-down automaton just cannot recognize. You get 100 push-down automatons, they cannot recognize it. Turing machine allows you to do fundamentally new things. Solve fundamentally different and new problems. But a Turing machine is now complex enough to encode itself. And once systems get complex enough to encode themselves, very strange things happen. Consequence of the halting problem is, provably, we cannot perfectly know the future. Because if I could perfectly know the future in this system, then I could intentionally break the future.
oh, that's cool.
In a similar way that this breaks. Because this space, it turns out, is complex enough to encode this space.
Are you saying,
Yeah.
Once a system becomes complex enough to encode itself, strange things happen.
is that implying that the universe we exist in today is somehow self-referencing?
Yes.
That makes sense. That's weird.
That was just an existential experience.
Okay. So, there's some ideas with that. All right, continuing. Completeness. Now, Kurt Gödel, probably the most famous logician of all time next to Aristotle.
Yeah.
We have what we call Kurt Gödel's completeness theorem. Now, Kurt Gödel proved that first-order logic, just wanted to show you that at least a couple times, that's what everyone calls what we've been doing, first-order logic. Propositional first-order predicate logic, everyone just calls it first-order logic, and if you ever read papers on logic, you'll see full all over the place. What does it mean? First-order logic. So, he proved that first-order logic was complete. What do we mean by complete? He proved that if Q logically follows from P, then it is possible to derive Q from P. It's possible to prove it. If it's true, it's possible to prove it in first-order logic. Makes sense so far? That one was probably something you would have guessed. It's pretty intuitive. If it's true, then yeah, there's a way to prove it. Now we have Gödel's incompleteness theorem. He then proved that in mathematics, any system of mathematics is incomplete. Meaning, there are true statements that cannot be proved. So up here we were talking about just in first-order logic. Here in systems of mathematics, they are provably incomplete. Now I have an asterisk next to that. Systems of mathematics, at least complex enough to encode basic arithmetic. Because he uses basic arithmetic in his proof.
Right.
And so he had to presuppose a system had enough to encode that. But all the systems you work with pretty much do. Euclidean geometry, yes, it checks it. The algebra you know and love, yes, it checks it. So these systems of mathematics he showed, are incomplete. There are true statements out there that cannot be proved. Next thing you would want to know is a system consistent? I didn't write that one up there, but there is a proof that first-order logic is consistent. We know that it is impossible to prove a contradiction in first-order logic. Now go into an actual system of mathematics, like arithmetic.
You can prove
In mathematics, he proved that if the system is consistent, then it is impossible to prove it's consistent. So if it's inconsistent, you can prove it. You just find a contradiction. But if the system is consistent, it is impossible to prove it is consistent. And that's what he proved. These are very frustrating things that he's proven for us.
Started not like this guy.
Yeah, there's a famous mathematician, Hilbert, and he was like, he would have probably been considered the greatest mathematician on earth in the year 1900. Big deal kind of guy. Definitely in the top 5, if not the best. And he was out to say, we need to prove three things. We need to prove that our systems of mathematics are complete, consistent, and decidable. Decidable meaning, if something's true, we can prove it. Kurt Gödel knocked that one out. Okay, well, at least show it's consistent. Nope, we can't prove it's consistent if it is consistent. So either it's not consistent, which, Hilbert, you're going to be very sad about, or it is consistent, we can't prove it, which you're going to be sad about. And then he says we need to show that it's complete. And Gödel showed that actually it's incomplete, and provably so. There are true statements out there that it is impossible to prove are true in arithmetic,
Doesn't that
and in geometry, and in all these fields of math.
if there are things that are true that can't be proven, doesn't that indicate that the process of proving things is incomplete?
If that's how you want to think about that word, incomplete, sure.
Meaning that we just haven't figured out, there isn't, the strategies of proving things hasn't been full, hasn't been complete. There's more ways to prove what is true that we haven't figured out.
It could mean that. I can't tell you what it means. I can tell you that it's the case. Now, of these, Kurt Gödel's incompleteness theorem, proving that arithmetic is incomplete, is far and away the most famous of these proofs. And probably one that even in regular culture you've come across before. So how on earth did he go about proving that mathematics is incomplete? Now, I can't show you exactly how he did it, but I can give you a taste of it. And that's the best I can do. And why we have that asterisk there for the system has to be complex enough to encode arithmetic. So how did he do this? First thing he does is he takes his system, and he's going to come up with an encoding of all the symbols in the system. So he says, left-hand parenthesis, we're going to assign that the number 1. The for all symbol, we're going to assign that 2. This is just random. This isn't actually how he assigned it. I'm just giving you a sense for it. He says, the symbol x, we're going to give that a 3. Right-hand parenthesis, we're going to give that a 4. ... Whatever the system is that you're working in, it has a finite number of symbols. Right? Assign each one of those symbols a number. Good so far?
What? I say the last thing you just said.
So, any system we're working in has a finite number of symbols.
Yeah. Like domain?
No, symbols. So over
Oh,
here,
symbols,
just the symbols used in the axioms and the definitions that you're using,
Okay.
has a finite number of symbols. Right?
Yeah.
Okay. So, there we go, first step. Assign each of them the numbers 1, 2, 3, 4, just counting up. Now, we need to come up with an encoding of all of our formulas. So, for example, you might have axiom 1 is for all x, blah, 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 some stuff about x. What do? We take 2, the first prime number, and we raise it to the power of whatever the first symbol was. What is our encoding for the left parenthesis? 1. So we raise 2 to the power of 1. What is our symbol for the for all symbol? 2. So our next prime number, we raise to the power of 2. Our next prime number, we raise to the power of whatever the next symbol was. And etc., going all the way down. Every formula has to be finite, and so this is going to just spit out some big number. Now we're doing prime numbers here because every number has a unique prime factorization. We're writing out the prime factorization of that number. And so what we're ensuring is for every formula, we have it going to one and only one number. Some formulas might be nonsense. Some of them are going to be actual sentences, but the point is we come up with a unique encoding for every single formula. These are massive numbers blowing up, just absolutely huge, but the point is, still just a number, right? And now you can start encoding all of your arguments. I go through the argument, I apply axiom 1, then definition 2, and then I show how those two together imply something using some other formula, and all the way down to some final statement. proving some theorem. Right? And so, how do we do the proof of that theorem? The first formula you use, you raise 2 to the power of whatever that number was. So A1 was this big product, humongous number, and now raise 2 to whatever that humongous number was. And 3 to whatever the second line of your proof was. And 5 to whatever the third line of your proof was. And it's going to give a unique encoding to your entire argument. And this way, for every single provable statement out there, we get some humongous number. And then the trick from here is to find a statement that is for sure not one of those humongous numbers that corresponds to a proof. And that statement will be a true statement. Find a true statement that for sure isn't any of those proven statements that you had before. And so it's going to be a true statement that's not proved. The intuition for what that statement is like is a statement like this. This statement is not provable. Question, is that statement false?
It's not provable, so I don't know.
If this statement is not provable. If it's false, that's not provable. Then it's provable.
So it's not a statement?
So then it's true. It's still a statement. So the statement is true. So he found, this is just to give you intuition. But he finds an actual big number with a big encoding. And he finds some statement out there. This gives you the intuition for what the logic is backing behind the statement. And the statement essentially says, this statement is not provable. If it was false, then it would be provable, so it would be true.
It reminds me of when you say, I am a liar.
It's kind of like that.
It's like, okay.
I only tell lies. True or false?
You could say that I'm lying, but then I'm telling the truth.
Yeah, self-referencing.
Or this statement is a lie is a different way to say it. Kind of like this statement is not true. Okay.
Yeah.
So this statement is not provable. Notice it's not that this statement is not true. The problem with this statement is not true, can't remember the guy who did the work with it, but he showed that true is not a concept that can be captured in any system. It's more foundational than that. There's no system that encodes the meaning of true. However, provable, that is now a word that means something to us. Provable means that you can come up with some series of statements such that they all logically follow from some derivation of it. That's what means to prove it. Proving is something that's real easy to check. We said that you can't have a computer generate a proof. It's real easy to get a computer to check that a proof is valid. Huge difference between coming up with a proof and just checking a proof. Checking a proof we can do. That's real easy. Coming up with a proof is a whole other beast. So checking proof, perfectly fine. So this statement is not provable. It's true. Here's the disturbing part of that. He found a statement that's true, and we can't prove it. There's no algorithm, no procedure that you can get to generate this thing. This is crazy. This means in our axiomatic system, here's A1, here's A2, pretend we're in geometry with all our axioms, right? It means that there's some statement out here, S, that is true in geometry and is not logically entailed by the postulates. And so this is a lot of mathematicians' great fears, is that they're trying to prove a statement that's impossible to prove, even though it might be true. Common one that comes up is twin primes. If you write out your numbers, twin primes are two prime numbers separated by a single number. So 11 and 13 are twin primes. They're two primes separated by a single number. 5 and 7 are twin primes. They're primes separated by a single number. The question is, one's not prime. The question is, are there an infinite number of twin primes?
They just don't know.
And it's been something that we've been trying to prove for a stupid amount of time.
Can you prove that it's not provable?
If the statement is false, then you should be able to prove that's false in your system.
Can you prove that you can't?
But if the statement is true, it could be the case that there's no proof that's true.
There's no pattern of primes, so we can't.
Can you prove that there's no proof?
No.
Oh.
Oh, yes.
Yeah?
Or of that particular statement, no, sorry.
Oh.
I don't know. The answer to that is I don't know. What we know is that there are true statements out there. Statements that we can understand are true. That is impossible to prove are true.
So are we proven that we can't find the pattern of prime numbers essentially?
No, so that one is still an open question. There could be a way to prove it.
Oh, okay.
But people have been working on it for so long, some people are starting to become suspicious. Maybe we finally came across one of these things that isn't provable.
Maybe I'm trying to solve a bug and I might not ever be able to solve
Well,
it.
the famous example used to be, what's his name?
Euclid's fifth?
No.
Oh.
Fermat's
Last.
last conjecture is what they used to call it.
Yeah.
Now they call it a theorem because we proved it. Fermat's final conjecture, Fermat's last conjecture.
Mhm.
What is Fermat's last conjecture? It's that. So, a to the 1 plus b to the 1 equals c to the 1. Can you find numbers a, b, and c that make the statement true? Yeah, easy. Make a1, b2, c3.
Yeah.
Okay, one of it's a squared plus b squared plus equals c squared.
Yes.
Can you find numbers that make that true?
I'm sure.
Yeah, you just have to think a little bit, but if we replace a with 3, b with 4, and c with 5, 3 squared plus 4 squared equals 5 squared.
Also 0.
Non-trivial solutions, so you don't get you 0, thank you. But numbers outside of 0, and we're talking about natural numbers. Okay, so now the question is, what about if I replace this with a 3? Are there any solutions to it?
I don't think so.
The answer is no. Similarly, if you replace it with the 4, 5, 6, any higher thing. So you can put 1s there, you can put 2s there, and that's it. 3 or higher, there are no numbers you can find that satisfy it. Fermat wrote that as a conjecture. People tried forever to prove it. It was kind of assumed that it was used as a problem that no one would ever prove for a long time
Didn't he
until
claim that he wrote the proof?
he claimed that he had a proof for it, but wouldn't fit in his margin. Everyone now pretty much agrees that he thought he had a proof, and he just had a mistake in his thinking. Because people do that all the time. They think, oh, I proved this, and then find out, nope, you were very, very wrong. Try again. So there were lots of people who thought they proved it, but they were wrong. There were lots of people who thought they proved Euclid's fifth.
Oh.
Anyways, I mean, just to give you a taste of it, there was an episode of Star Trek where, what's his name, bald guy, Picard, is still working on the problem. Because Star Trek came out before Wiles, I think is his name, solved the problem. And so it's kind of assumed, here's one that we're never going to solve, even in, I'm not sure when Star Trek's supposed to occur, but.
Just be sure they did solve it.
It's like,
Yes, we now are, oh yeah. When someone thinks that they have a solution to that, everyone is going over it with a fine-tooth comb. It was a big deal.
Huh.
So, yeah. Now the amazing part is that we can understand that the statement is true, but it doesn't have a proof. And so what this shows is that human understanding is something more foundational than something being provable.
yeah. Or,
Maybe we just have
We can understand proofs, but our understanding is not limited by proofs.
I think I'm
And this has applications for like AI. Common thing is AIs are going to overtake humans. AIs blah, blah, blah. AIs can't do that. They can't do what Gödel did. AIs don't know how to go outside of axiomatic systems.
they can't think about themselves.
An AI can only apply logic. Ultimately, a bunch of logic circuits. That's all it can do. Applying logic to these axioms, you can't get the statement. It's not possible.
Can they kind of, I don't know.
What's his name? Famous physicist. Not Hawking, but he worked with Hawking. I always forget his name.
I don't know. I would know if I did.
Don't let me space this. I can picture the guy. He's been knighted, I think. Penrose. Roger Penrose.
Oh, Penrose.
Roger Penrose, he has a whole book called The Emperor's New Mind, going over his explanation for why human understanding is not a computation. It's not a matter of maybe one day with super advanced no.
What's it called?
The Emperor's New Mind. And then he has a newer version of it, but I can't remember the newer version.
I think for our brains to solve that, I'm pretty sure we just bring it to a shortcut, and it doesn't actually turn out to be true.
It turns out to be true. We're very sure that's true, and we're very sure that's not provable. We are more sure that this is true and this is provable than we are that we built computers correctly.
Perhaps it's a coincidence.
Even if it's a coincidence, it's true, and it's not provable. Both those things are the case.
So does that mean that?
And I wanted to give you a taste for the thinking that goes behind this proof. I thought I'd have time, but we're running out of time.
Wait, quick question. Doesn't that mean that an AI wouldn't be able to simulate a human perfectly?
It's more foundational than that. There is no axiomatic system that encodes the human mind.
So you could
No axiomatic system can get this.
right.
Humans can understand that.
So you cannot perfectly replicate the human mind in a computer.
In any axiomatic system.
Especially not something.
Forget limiting it to the finite axioms that you use in computation theory to come up with your definition of computation.
Right.
You might be thinking, oh fine, our current definition of computation. Maybe some new axiomatic. No axiomatic system. We would have to change it more foundational than changing what we mean by computation. We would have to come up with new ways of talking about bodies of knowledge in general. Something more foundational than using logic to construct these axiomatic systems. And what that would be and how to even remotely think about that, I don't know. I don't know how to get more foundational than logic.
Never heard of AI to discover something new. It just simply regurgitates what's already.
Well, now you're just thinking about like something like ChatGPT.
Yeah.
Exactly.
We have used AIs to help us prove theorems, faults,
Yeah.
a few times.
That's cool. Right?
And we've even used AIs to help us prove theorems that are true. Oftentimes to prove a theorem, you have to break it down into a bunch of cases. Occasionally, working through all the cases is kind of tedious, and it's easier to write a program to iterate through the cases for you to check them all. So we've used AIs to help us prove things all the time. AIs can prove things, but there is no general procedure to generate proofs in general. And then there are things out there that are in no way entailed by the axioms, and yet are true in that axiomatic system.
Could you have an AI?
Very strange.
Could you have an AI that had the ability to prove an entire axiomatic system?
No,
What about?
because an axiomatic system,
Yeah.
finding universally valid statements in a system is undecidable. In other words, let's say we have at work, you've got some particular statement, and you say, Mr. AI, I want to know, is this statement true? And it starts turning away. And if it finds it, it's going to halt and stop and tell you, I found it. The question is it going to halt? Can you prove that's going to halt? Knowing whether or not that computer is going to halt, forget what the input is already impossible in general. And so you can never tell the difference between you gave it an impossible task, and it keeps just checking, versus you unplugged the second before it was going to be done.
Yeah.
You said after 1 trillion years, okay, it's not going to find it. It needed 1 trillion years in 1 second. You just stopped too early. And there's no way for you to know the difference between those two scenarios. So you can see how it comes back to the halting problem.
Yeah, I see. That's cool. That's cool.
And I don't know. We can't. It's too much of a tangent. We're going to have to skip this for next time. Unless you guys really want to know about it. I was going to prove to you that there's the same number of naturals as there are integers. So the naturals are 0, 1, 2, 3. The integers are -3,
Yeah.
-2, -1, 0, 1, 2, 3, going on forever both ways. So I was going to prove to you that there's the same many of those as those, and that there's the same number of integers as there are rationals, rationals being all the fractions you can write.
Yeah.
But there are not the same number of rationals as there are real numbers.
I've seen it.
And the proof for how those aren't the same uses what we call diagonalization, which is the logic behind how Gödel does this. I can't take you through his proof, but I can give you the basic logic that underlies it, which is basically list out all the provable statements and then find a statement that for sure is not on that list. It's very similar to finding a real number that doesn't show up when you do diagonalization if you already know the method.
I remember you proving this, and I'm just kind of curious how this applies. If you could just tell us.
The logic that is used here is similar logic for how Gödel proves his incompleteness theorem. He uses the thinking of diagonalization in there. So I was going to give you the heart of it the same way that this kind of gives you the sense for what we mean by undecidable.
Okay.
That's as good as I was going to do. We can't do the full proof. It would be its own thing.
Yeah.
I mean, we could if you guys really want to, but that would be dedicating a few classes to it.
Oh, wow.
I don't know how much time it would take. I'm guessing a few classes. I really don't know. Because you'd have to get familiar with the axiomatic system that he's using before even going into the proof. Because he uses Peano's axioms. And I could probably find like a simpler one that does it. I don't know. I'd have to go looking. I haven't done that much searching into it. But I'm suspicious it would be a couple class detour.
Is there anything new in logic that we're looking to prove or find out about?
There's
Like,
like,
I know.
This seems like a pretty major breakthrough. in
there's like
terms of
20
logic.
This was a major breakthrough.
So what?
You go from the year like 1850 to 1950.
Uh-huh.
Physics blowing up. You had Maxwell's equations coming out in that time. You had special relativity, general relativity, the atomic theory, Boltzmann, Einstein, quantum mechanics, quantum theory being done. What Einstein died working on is still the problem of modern theoretical physics. How do we combine the Standard Model and general relativity? There hasn't been big breakthroughs since then. Same thing with logic. All these breakthroughs in logic that we're talking about with Kurt Gödel, early 1900s.
Are there logic problems that we're working towards? Like, do we have
I don't know new research going on in the field, but it's nothing like what was these breakthroughs constantly over and over again. The complete new way that we axiomatized systems was all going on early 1900s. We're using Hilbert's axioms in geometry. Hilbert, when he wrote those axioms, early 1900s. You talk about the breakthroughs that went on in mathematics, physics, logic, computation theory. Alan Turing, computation theory, literally, in that whole time. Went from not being a field to where he left it is pretty much where it still is today.
Well, we've had some breakthroughs in physics today around Hawking and stuff like that.
But not introducing entirely new fields.
I see.
And it doesn't even compare to Einstein coming along and saying, hey, guys, general relativity.
Yeah.
We're coming along, hey, quantum mechanics.
that was-
Or Maxwell, hey, 4 equations, all of electricity and magnetism, right here, boys.
Yeah.
It's nuts.
Are we gonna?
So, 1850s and 1950s, what was going on intellectually, it's just astonishing. So I don't know that we'll see groundbreaking explosions like that again.
Well, I don't see why we couldn't.
Well,
We had
people
Plato-
make their arguments for it,
We
but
had Socrates, Plato, and Aristotle in a row.
I think with all of our computational power, we still can't compete. Is interesting.
Well, it's kind of the point. It takes more than computation to describe stuff like that.
All right.
That's interesting. So like almost
So-
every human function.
Any other questions for any of this? That was kind of a weird detour. Next time, we will be introducing the existential quantifier, that backwards E, and then doing proofs that use it. So we'll go back to just get what are the 2 rules introduced, going back to our rules of logic, and just going back to doing simple proofs. Good? Cool. See you guys next time.